Good afternoon. My name is Nick, and I'm here today with Adriana, Nelson, Paul, and Andy. We are Team Pure, and we are designing a water purification system for developing countries. Now, water is something that we all take for granted, whether it's leaving the shower running to get warm, or the number of water bottles that can be found at a local supermarket. We live in a society with an abundance of water, and this allows for us to live our lives without ever wondering where our water comes from, or more importantly, if our water is really clean. This differs greatly from many other regions around the world. Many communities in developing countries do not have this luxury and are forced to drink and use whatever water they have access to, regardless of if it's clean. And this leads to many communities being plagued with waterborne diseases. 2.5 billion people around the world do not have access to clean water, and over 3.5 million people die from waterborne diseases each year. We have focused our project on a country where there's both a severe waterborne problem with waterborne diseases and access to stakeholders. Ghana is a sub-Saharan African country that suffers from many waterborne diseases such as Cryptosporidium, Giardia, and E. coli. With one study regarding water quality in the greater Accra area mentioning Cryptosporidium being identified in 63% of tested water sources. Over 20 million people in Ghana do not have access to safe drinking water. 25% of all deaths under the age of 5 are due to diarrhea. 80% of all diseases in Ghana are caused by unsafe water, and 87% of the country does not have access to sanitary water. Now, we've been fortunate enough to be able to interact with stakeholders who live in Ghana, as one of our faculty advisors, Dr. Eki, has put us in contact with 2 professors who work in Kumasi. Our stakeholders are fortunate enough to live in urban societies in Ghana, where some minor forms of sediment purification exist. Unfortunately, rural areas do not have the access to these same luxuries, so many people are forced to take water from boreholes or rivers and use it with no filtration whatsoever. Due to this, our project is catered around providing water purification to these rural communities through communal water storage tanks by being implemented at the outlet of these massive water tanks and purifying the water before it reaches the end user. I'll now hand it over to Andy to go over system characteristics.
Thanks, Nick. So based on our conversations with Dr. Eki, Dr. Mensah, and Princess, we developed these system characteristics grouped into 3 buckets of accessibility, usability, and durability. The ones that we want to highlight are a fixed cost of $300 to make the unit accessible to these communities and organizations based on their budgets. We also want the throughput of our system to match the existing output, meaning providing 150 gallons per day at a 0.2 gallon per second flow rate. Our system should also accommodate a 10-year maintenance schedule and a 25-year lifetime. Now, there are a variety of existing solutions on the market. Membrane filtration is a very high cost. Slow sand filtration has a very short maintenance cycle. Solar disinfection has a limited water throughput due to its long exposure times. And lastly, chlorination, one of the most common methods, isn't effective against Cryptosporidium, which is one of the major causes of these waterborne illnesses. For these reasons, UV disinfection was chosen as it's the most effective form of water purification that suited our characteristics. UV disinfection works by shining a high-intensity UVC light, specifically the germicidal wavelength of 254 nanometers, that essentially deactivates microbes by scattering their DNA and RNA. Here will be a self-contained filtration system that will interface directly with existing communal water storage tanks. Since microbial growth is very common in these storage tanks due to stagnant water, Pure will serve as the last purification touchpoint. As seen on the right, the water will flow from the storage tank through a sediment filter, trigger a flow switch that turns on the UV light, and finally flow along the UV light in the reaction chamber to the outlet. As seen on the left, the system will be powered by a solar cell on top of the wooden enclosure and be able to accommodate buckets and jerry cans underneath. To retrieve water, the purge valve of the filter must be closed. Open the ball valve to start the flow and close it to stop the flow. To purge the accumulated sediment from the filter, the ball valve leading to the reaction chamber must be closed and the purge valve opened. The flow will purge the sediment out of the bottom of the filter. This should be done for around 5 seconds or until the filter is clear. An RGB LED will serve as the system health indicators. A green LED means the system is on and functioning properly. A yellow LED means that the UV intensity has begun to deteriorate. Finally, a red LED indicates that the intensity is under a safe limit for purification and the bulb should be replaced. To replace the UV bulb, simply open the top of the enclosure, unscrew the lid of the reactor, pull out the bulb and disconnect the 4-pin socket, plug in the new bulb, close the system, and you're all set. I will now pass it on to Nelson to discuss our system characteristics.
Thanks, Andy. The system is broken down into 3 components: a sustainable power source, a UV light, and a water chamber. First, I will be discussing the sustainable power source. Looking at the concept selection process, we used the World Health Organization numbers for daily water consumption estimates and calculated that 37.5 watt hours would be required to power the light each day. Afterwards, the power source was picked from 4 choices: Solar power was the only one that fit all of the criteria needed for the system to function. Next, looking at the schematic, the solar panel is attached to the charge controller and the battery. The energy from the panel charges the battery and powers the Arduino and UV light. A relay switch is connected directly to the battery to turn on and off the light based on the flow meter connected to the Arduino. This results in the light only being turned on when the flow meter is activated. The solar panel testing process looked into sunny and cloudy days to see their effects on the energy generation capabilities. The data collected during testing and after forecasting both cases showed that the solar panel is energy positive with a safety factor of 3.5 times on sunny days, 1.1 times on cloudy days. The panel now has two settings: lie flat for easy transportation and angled for optimal power generation. It is currently configured for the northern hemisphere at 55 degrees and will be adjusted to 25 degrees to suit the optimal angle for operations near the equator. Next, I will pass it off to Paul to discuss about the water chamber.
Thanks, Nelson. The UV light has to be separated from water flow while also allowing light to pass through. We investigated 3 materials used for UV protection and settled on a quartz sleeve that easily transmits the desired UVC light. We also investigated reflective materials to enhance the performance of the water chamber. We investigated 3 materials that were most easily adaptable to our chamber geometry. Aluminum tape was chosen based on its reflective properties, flexibility, and price point. We wanted to use readily accessible materials to build the chamber and thus selected Schedule 40 PVC. Given all of the diameters we investigated met the expected exposure requirements, we used a combination of 2-inch and 4-inch PVC. The upper chamber will be 4-inch PVC to allow for a larger storage area for electronics, and the lower chamber will be 2-inch PVC to increase the UV interaction with water. The system was waterproof to ensure the electronics would be safe and dry at all times. We sealed all the chamber connections using PVC cement, and the electronics were separated from the water chamber inside the enclosure. The lid was also fitted with a weatherproof gasket and latches to ensure the system would not be harmed by any external elements. I'll now pass it off to Andriana to talk about the ultraviolet light.
Thank you, Paul. Due to the fact that there's suspended particulate matter in the water that we will be treating and that these particulates will significantly decrease the UV intensity, Pure has decided that we will need to incorporate a filter in order to effectively purify the water using UV light. We looked at a variety of filters, with a sediment backwash filter being very effective, but also having a high cost. Then we looked at carbon membrane filters, which while low cost, require frequent maintenance. So finally, we settled on a mechanical spin down filter, which is inexpensive, effective, and easy to maintain. In order to test the turbidity, first we mixed various samples of potting soil and water. Then we passed these through a spectrometer to measure the absorbances. Finally, passed these through our filter to test the efficacy. Looking at the results, we tested a 100 and 1000 mesh filter, which correspond to particulate sizes of 150 microns and 15 microns respectively. As you can see from the data, the 1000 mesh filter had the lowest absorbance, which means it'll have the highest UVC transmittance. And there's also a very clear visual difference in the water quality. In order to test the UV dose, first we looked at the exposure time, which is a factor of the flow rate, as well as the UV intensity, which we measured using an off-the-shelf UVC meter. We measured the intensity of the bulb at the light source, at the 4-inch diameter and at the 2-inch diameter. And taking these results through air and through water, as well as the calculated exposure times, we can calculate a UV dose administered of 28.9 millijoules per centimeter squared. When comparing the administered dose of our system to the required UV dose to inactivate various pathogens, you can see that our system successfully does this, including a safety factor ranging from anywhere of 2.9 to 5 times. When looking at Cryptosporidium, one of the most prevalent pathogens, you can see that the dose given by our system is not quite high enough to inactivate the pathogen. So moving forward, we'll have to make some changes. First, we can switch out the UV bulb to have 2 times the intensity. We can also increase the exposure time by including a flow restrictor. And finally, we can decrease the radius of the water chamber in order to increase the interaction with the UV light. Here are photos of our overall system. On the left, you can see the enclosure, and on the right-hand side, you can see pictures of where the electronics and water chamber are housed. Additionally, there's photos of our customized 3D printed part that we use to secure the chamber, as well as the dual cap system that we used to safely secure the quartz sleeve and UV bulb. In this video, you can see the system in action. So there's dirty water that's being pumped up. It then passes through the spin down filter and then eventually goes through our water chamber and comes out clean and purified. Take note of the green indicator light that is on, which signals the fact that the UV bulb is actually working. Finally, we'd like to thank all of our advisors for their help throughout this entire project. Thank you so much for listening to our presentation.